So we'll continue on with yesterday. We've just got 2 questions to go over 6H, question 4 and 5. So we pull our notebooks out. There should be some blank space on the page overleaf, page 50. So I intentionally left a bit of space there given we've got 5 questions, so if you need space, it's there. Okay, so we have a plane in space. It's got x plus ky plus z is the direction of the normal. And we don't know this value of k, and we're saying find the value of k such that the plane contains this line. So if you think, right, we've got a line in space, and we've got a plane. I'm going to draw a rectangle to represent the plane. And we want to find the value of k such that the plane and the line are parallel, they're existing together. So what we're effectively doing is transforming the plane. And so if the line lies on the plane, if the plane contains the line, you can think of it like this, okay, that the line is on the plane. So the way we're going to do this is we can subtract the direction vector of the normal, okay? If this is the plane, then this is the normal, and the direction vector of the normal is going to be 1, k, and 1. And all that is the coefficients of the x, the y, and the z term. All right, that's the direction vector of the normal to this plane. Now, if this plane contains this line, what's going to be the angle between the normal and the line? If the plane contains the line, what's going to be the angle between the normal and the line?
90 degrees.
90 degrees, which means, how might we solve this? Who's got an idea?
What's the rule?
What's a property yet?
Cross product.
Dot product, yes, correct.
Same thing.
Correct. Correct if you said dot product. It means the dot product of, now what am I going to subtract from this line here? We want the direction vector of the line, right? So we have -2 for the x value, 1 for the y value, and 3 for the z value. And so we want the direction vectors to be perpendicular, and they're perpendicular if the dot product is 0. So we'll apply the dot product here. We'll have -2 plus k plus 3 is 0. And solve through. This gives us k plus 1 is 0, k is -1. All right, so that's the answer to question 4. Find the value of k for which the plane contains the line. So we're just thinking, oh, that'll be when the line is perpendicular to the normal. Very good. Okay, let's move on to question 5 then. And we're going to introduce some terminology to you here. And we're also going to do this question in a long way, although there is a formula for it at the bottom of page 48 that you can apply a bit later, but I'll just explain the reasoning behind it. Find the coordinates of the foot of the normal from this point to this plane, and hence find the shortest distance. So here we have a plane, and the equation of the plane is 2x plus 3y take away z equals 7. That's the equation of the plane, and we have some coordinate that's sitting above the plane. Okay, it's not sitting on the plane. And the coordinates of P here are x is -1, y is -2, and z is +2. All right, so I've sketched it there. Find the coordinates of the foot of the normal. So what that means is the normal can be drawn from anywhere on the plane, right? The normal is just a line perpendicular to the plane. And so that means it's going straight up to that point. All right. So our question is, what is the coordinates of the foot of the normal, where this line meets this plane? All right, that's the foot. The foot you can think of as like the foot of a person. If that's a person standing on the plane, that's their foot. Okay, so how are we going to find this coordinate? Well, let's call it F for foot. It's going to be coordinate F. And the line through PF. Let's come up with an equation for the line from P to F. Okay, so we need 2 things for the equation of a line. Let's do it in vector form. We're going to have a coordinate. So the coordinate we start with is P, plus some parameter T. multiplied by the direction. Who can tell me, what's the direction of PF? Oh. Yeah, it's straight up, isn't it? Yeah, yeah. So how can I know what the direction vector of this is? What is this? This is the equation of this has the same direction as the 90 degrees, so it's the normal. All right, so we know the direction of the normal is going to be 2, 3, and -1. So let me just explain that, make sure we understand that. We've got some coordinate P. We want to know what's the direction vector of PF. Well, PF is perpendicular to this plane, and so we know from if this is the equation of a plane, then the perpendicular vector has direction 2, 3, -1. That's the definition of the equation of the plane. Okay, hence, so we still need to find the coordinates of F. So this is the line from P to F. I shouldn't write vector notation, sorry, it is the line PF rather than it being a vector. Now, this line, PF, is going to meet this plane when the line satisfies the plane equation. So let's move from here just quickly to parametric form. We've got the x value is going to be -1 plus 2 lots of t, y is -2 plus 3 lots of t, and z is -2 take 1 log of t. We're going to determine the value of t such that the line is on the plane by putting in the x value in here, the y value in here. So let's process that. Okay. This line will meet this plane by substituting in those values and determining the value of t for which the line meets the plane. All right, let's solve through for t. We're going to expand and collect like terms. All right, so step 1, expand everything. Then we'll collect our t's. We've got 4 plus 9 plus t is 14t. And then I've got -2, -8, -10. Plus 10 to both sides, and then divide both sides by 14. Alright, so that's not a very nice value of t, but that's okay, we can still solve through. Thank you. So, this is our value of t for which this line meets the plane. We're going to plug the value of t in here to determine the coordinates. Alright. So, when t is 17 on 14, x is -1 plus 2 lots of 17 on 14. So I'll just process it here. Plus 2 lots of 17 on 14. We've got 10 on 7 for x. We've got 17 on 14, 23 on 14 for y, and 2 take 17 on 14, we've got, 11. Okay, so we've got those coordinates of x, y, z. This is the coordinates of the foot of the normal, all right? Cool, okay, so that's the first part. Find the coordinates of the foot of the normal, done, and hence find the shortest distance. Well, the shortest distance between 2 points is always a straight line. This is a straight line here, so we want to find, I'll write the coordinates up here for f, 10 on 7, 23 on 14, 11 on 14. We want to know what is the distance between these 2 points, all right? What we would do, what I'll do in a sec, we'll find vector PF and find its modulus, okay? What is the vector from P to F? and what is its distance. All right, so we'll do the coordinates of P, take the coordinates of F. All right, so there's a little bit more involved there with fractions, but the operations are the same. I'm just going to write out our syntax for that. Let's find vector PF first, and then we'll write the modulus of it. So the vector from P to F will be -1 take away 10 on 7. Sorry, other way around. 10 on 7 take away 1. And then 23 on 14 take away -2. And then 11 on 14 take away 2. Okay, so we'll be processing those. Take away -1. Processing those and then finding the modulus of it by squaring and then square rooting. Okay, so both of those okay? Any questions about that process there? So just with question 5, we've done a long way of doing it, right? I found PF and I've sort of explained to you a way of arriving at the answer using processes we're familiar with. Right at the bottom of page 48, there's a formula to evaluate question 5, okay? The shortest distance from a point P to a plane is given by this equation, okay? So you can have a go at applying that. I just wanted to explain the reasoning behind how we can arrive at a formula like that. Obviously the formula will be a lot faster. Very good. All right, any questions about that? Cool, okay, so let's